Yeah, what I'm really trying to focus on is the interpretation of the mean, variance, and standard deviation. What does it mean? Like, I can give you the formula, I can show you how it's done, and you'll probably be able to do it. But the reason why students will find it difficult when it comes to the exam questions is because they don't know what they're looking for. They don't understand what the application really is. So if I spend a bit of time just describing why the rule works and what you're really trying to find, like I said, it translates to all the other topics, okay? So that's our aim. If you really didn't understand what I'm saying, either watch the video again or look at exercise 13D. It describes every one of these terms in the exercise book really well, okay? It gives you the proofs and it tries to describe it visually as well, okay? So let's have a look. Discrete random variable. This goes back to year 7 when you first learnt data. It goes under interpretation of data. And at the time you had two types of data. You had quantitative and qualitative. Qualitative was anything that was non-numerical. So like colors. You know, you can have, what's your favorite color? What's your favorite ice cream? You would say strawberry, chocolate. That's not a number, okay? But you can get a data out of that. You can see how many people like ice cream, how many people like chocolate flavor or vanilla flavor. So that was falling under qualitative. Under qualitative, you can split that into two different types. You had ordinal and nominal. Ordinal meant that there was an order to it. For example, small, medium, large. It's not a number, but there is a rank. Okay, you got, and then you got your nominal data, which means or categorical. In that sense, it doesn't have a order. It's just a name. So like chocolate or sports, like you could say tennis, table tennis, badminton. There is no order. There's no ranking in that, but it is not numerical. So we follow that under qualitative. And then you go into quantitative, which is numerical, which is what you're doing now. Numerical data, which then is split up into two types. There's continuous and discrete, which is what you're learning in year 12 right now. You're sort of applying that idea. And discrete is how I describe it as anything, the type of data that you're dealing with is countable. What's countable? Number of students in this classroom. If I had to count you, it will be 1, 2, 3, 4. It's countable. If I had to talk about shoe sizes, okay, so we have shoe size or foot size, you got your 12, 12 and a half, 13, 13 and a half, but you never go into a store and say, I want 12 and 2.78 for my shoe size. Okay, it doesn't exist, so it's countable. So you can count that. You can count the number of chairs in a lecture theatre. You can count the number of people with brothers and sisters. How many brothers do you have? How many sisters do you have? So it's all countable. We call this discrete random variable or discrete data. It's a type of data that we use and the reason why you need to know what type of data it is because it makes a difference on how you find a probability. So for example, if I gave you in terms of a discrete data right now, if I said, what's the chances of me picking someone randomly here that is male? Then what you do is you count the number of students in this classroom, so you find out the total number of students, and then you count, well, how many males are there? And then you put your number of males. And so therefore, probability of male equals to, by counting the number of males out of the total, and it gives you an answer. True? So it makes it pretty easy. But then the type of data, for example, if I said there was a string that was 6 centimeters long, okay, so there's 0 to 6 centimeters long, and I asked you, what's the chances of you cutting this string with the scissors, randomly cutting it? What's the chances of you cutting exactly, let's say, 4.51 centimeters? If I asked you to find the probability of that, see, what's the issue here? The issue is in the sense that if I ask you to find the total, well, it's infinite. You can't find the total. You don't know how many intervals there are. If I had told you there were 10 intervals, yes, you can figure that out. But right now, you don't know what the intervals are, and I'm asking you for 1 point. So it's 1 out of, well, we don't know. This is categorized as continuous because there is no countable data. So how would you work this out? Well, if I had told you to find out the probability, what's the chance of you cutting anywhere between 0 to 3 centimeters, you could tell me. You would say that's 50%. But how did you know it was 50%? Because you took a region. That's why in continuous probability, you will be dealing with area. Areas will talk about a region. That's the difference in approach, but the concept's the same. You're still finding total, which is 6, and you're dividing it by an area, which is half that area. 3 is half of that 6 area, which is why you can get your favorable outcome divided by total outcome gives you a probability. That's the difference between continuous and discrete. That's why you need to know the difference between when do you use which one. And that's why I said the concept stays the same, but it applies differently for every topic. You got to know when you use it. Okay, and in your exams, they'll hint it out in the wording of the question and little keywords. That's when you know which type of probability or which approach you would use. Okay, that's the difference between them. All right, so now we know, okay, discrete is anything that's countable. Let's look at, well, now that we know the data, we know how to find the probabilities, favorable outcome out of your total outcome. That's pretty straightforward. Let's move on to the next term that I said that you had to understand, which was called expected value. You've learnt expected value back in year 7, 8, 9, which is called the mean. You learnt the mean back in primary school, which is called the average. To find the average, it's a sum of numbers out of your total, out of number of numbers. That's how you would have done it. The expected value, if you don't know, in terms of probability, when we say the expected value, we're just saying, what do we expect in the long-term average? Now, the example I'm giving here is I'm saying, if I flipped a coin, I know there's a 50% chance of getting tails. If I flipped it 1,000 times, and I asked you, what's the chances of me getting, how many, out of those 1,000 flips, how many of it will be tails? If you knew there was a 50% chance, what would you expect? 4. I would hope it'll be 500. And what you just answered to me just now, that is on average. Like literally, if I actually flip, or even if I said if we flipped it 10 times, and I said, what do you expect in terms of tails? You would say 5 out of the 10 would be tails. But if we actually did it experimentally, it's not true. If I actually gave you a coin now and said flip it 10 times, let's say we actually get 5. We don't. But what we expect is something that we think in the long term, which is true. In the long term, if you do flip infinitely, the chances do come out to be 50-50. But in a small sample, like 10, you won't see that. It might be someone might get 7 tails and then 3 heads, or maybe actually they will get 5 out of 5. Okay? But that's really irrelevant because it's such a small data, which if you apply it into real life, this is why when they do surveys and whatnot, they need a large sample. The larger the sample, the more accurate the data. Okay? And in our case, we use the average or the expected value or the mean to predict. What do we think? With our data so far, what do we think that implies? That's where the mathematics comes in, where we expect, we predict what amount, how much of an amount should we get on a percentage. Okay? So the question is, I said it is the long-term average. I said the average is the sum of all numbers divided by a number of numbers. Let's do an example. Let's look at this one. The mean or the expected value started off from gambling. The idea of, like for when you're gambling, you're likely to gain profit or not. So let's have a look at this one. Let's say a person may buy a lucky ticket for $1. Okay, so they buy it $1, so they're spending $1. They have a 20% chance of winning $2, meaning they make a profit of $1. Or a 5% chance of winning $11. So they have a chance of making a profit of $10. Now the question is, and if they don't, then otherwise they lose, so they lose $1. Okay, so they spend $1, they either win $1, or they win $10, or they win nothing, so they lose $1. Okay? Now the question is this a good game to play, given the percentages? So how do you know? How do you know, like, you could spend $10, and you never know, you might gain $20, because there's a 5% chance of that happening. Now I know it's low, but if we played the game 1,000 times, is it a worthwhile game? How do we know? What's our profit like? Are we gaining or are we losing in the long-term average? So then, if I now asked you to find a long-term average, this is what we're going to use. We're going to use sum of all numbers divided by number of numbers. Yeah. So I told you the profit was either you got 20% chance of gaining $1, you got 5% chance of gaining $10. Or you have 75% chance, because that's 20 plus 5 is 25%. So you've got 75% chance of losing $1. Let's work out the actual average for this. So I said, hypothetically, if we were to play 1,000 games, I'll put it all in the table, P for profit. So I'm just going to write here, profit. You either lose $1, we worked out it was 75% chance. That's the probability of P. Okay, that's the notation for it. They're just saying the probability of the profit being losing $1 or losing or gaining $1 or 10. That's what the little p is. That's how we write our notations, because we're saying the profit equals to whatever this is. Okay, so that's what the notation is, and you do have to get used to writing and using that notation there. Okay, so the chances of it being losing $1 is 75% chance. Chances of gaining $1 is 20% chance, and then chances of you gaining $10 is 5% chance. Yeah. Now, if we played 1,000 times, if we play this game 1,000 times, 75% of 1,000. What is that? Out of 1,000 times, how many times would I expect to lose $1? How many times? What's 75% of 1,000? 750, thank you. Okay? You can do 0.75, if you didn't know, 0.75 times 1,000, just move a decimal point, that gives you 750. Okay? So, we know there's 750 times that you're going to lose $1, so let's list it out. You would expect to lose $1 750 times. You would expect to win $1 200 times. You would expect to win $10 50 times. Now, if I ask you to find the average, just to know, am I gaining or am I losing in this thousands? This is what I'm expecting. In 1,000 games, am I expecting to lose or gain? So if you think about it, if I'm losing $1 750 times, you would say, well, that means lose $1 plus lose $1 plus lose $1 plus lose $1, and you add all the sum of all numbers divided by the number of numbers. Now the total numbers I have is 1,000. I've got 1,000 of these data. I've got 750 plus 200 plus 50 gives me a total of 1,000. Now I want to know my profit. That's what I'm trying to find. I'm trying to find my expected or long-term average in terms of my profit. So my profit was either lose $1 or again $1, and I got 200 of them. And I also potentially have $10 where I gain 50 of them, and it carries on, right? Now there has to be a quicker way in solving this. When you're working out, if you know that you've got 750 times that you've lost this $1, well, it's just 750 groups of losing $1, or -1. So that's just 750 times -1, which means you'd lose $750. Yeah? So if I had to write this out as an average, I'm just trying to show you the mathematics. This is the average. That's how you would find the average. Now I'm trying to show you why I have this. See, when I write this, the average profit, I'm just saying this is the sum of all numbers, which is 1,000. So number of all numbers, this is the sum of all numbers. So right there tells me I've got -1 plus -1 plus -1, 750 times. This one tells me I'm gaining $1 200 times. So 1 plus 1 plus 1 plus 1 plus 1, 200 times. And then this one tells me I've gained $10 and there's 50 of them, so 10 plus 10 plus 10 plus 10, 50 times. So in total, if you work that out, you've actually lost $750 plus $200 plus, what's that, 500. Work it out. That means you get 50 out of 1,000, minus 50 out of 1,000, minus 50 out of 1,000. And so that implies, if we work out the percentage of the probability, -50 out of 1,000, which is the average, implies that I'm losing 5 cents for every game on average. Okay, not exactly every game, but on average. In the long term, this is why the expected value is called the long-term average. On average, I'll be losing roughly 5 cents per game. okay, in the long term. So that would imply that this is not really a worthwhile game because in the long term I'm not really winning, I'm actually losing. But what I want you to see, which is why I'm showing you the average and why it works, because you've done the average since grade 6 all the way to 7, 8, 9, what I want to show you is why this formula comes about. Now, this is the notation which I want you to learn. This is the notation for expected value, and we define P as the profit. Okay, so this is expected value, meaning the average, and this is the profit. So you're just saying the expected value is negative 0.05. Now what I want you to see is if we look at this equation, let's think about it. If I split this fraction up, this is negative 1 times 750 out of 1,000 plus positive 1 times 200 out of 1,000 plus 10 times 50 out of 1,000. But what we can see is 750 out of 1,000 is 0.75. We can see that 200 out of 1,000 is 0.2. We can see that 50 out of 1,000 is 0.05. So what am I trying to say here is I can say that that means I can rewrite this equation as negative 1 times the probability of getting negative 1. Or the better notation for it is PR of capital P equals negative 1 plus profit of $1 times the probability of getting P equals 1 plus 10 times the probability of P equals to 10. Which is really just, if I had to write this as a sum, the probability sum, I'm summing all of my x variables, so this is my variables, that's my data, negative 1, 1, 10, it's countable, discrete variable. Sum of that multiplied to the probability of x. That should give me the expected value of x, which is the average. Now I know I could have gave you that rule from the beginning and you would have been able to answer this question just by multiplying these two and then add them together, and that tells you expected value, but it loses the concept. Why does it work? And what does it mean? So all you're trying to find when you say the expected value, and I give you that formula, it is just to find the long-term average. What do you expect in the long term? That's all you're really trying to do. So this is the formula that's in your textbook, and they're saying the expected value, which is your average, your mean, is equal to the sum of your x variables, which is your discrete random variables, multiplied to the probability of that variable occurring. That gives you this. Okay? And that's just trying to tell you that this is just to find the average. So I didn't want you to look at this and go, I don't understand, but I'm going to memorize this. You don't have to memorize it, because it all makes sense from your average. Okay? And that's where it sort of starts. The expected value is just to find the average, to find the mean. There are some properties on the expected value, which I'll talk in the next lesson about the properties. For now, I just want you to take that formula down and understand that is to find the average or the mean. Okay, long term, what do you expect? Okay. All right. And why do we want to know the average? Because the average implies or tells us whether it's a good thing or bad thing. So for example, if I said on average that our class gets 90% for our SACs, that's very good, because that means that every one of you, even though you're not getting exactly 90, but if I had to add all your scores together and shared it, every one of you had to get one score and every one of you have to be the same, it's 90. That's why it sounds high. That's why it's a very good average. And that's what the average implies. The average can give you, it gives you an interpretation what to expect in this thing. So in this case, our game, we know that we're losing 5 cents. Oh, 0.05. Thank you. Sorry. There we go. Thank you. Okay, and if you're wondering whether the number of times you play matters or not, it doesn't. because I could have said 10 times and it still would have been 7.5 times out of 10, so it still would have been the same percentage or probability. Okay, so I just chose 1,000 so it makes it easier for you to understand. Okay? All right, let's go into the next part. So, this is your expected value. It describes this in your textbook. They also have the proof for it as well. But the one other thing is that notation is also the expected value. Okay, so that's why I wanted to point out this is if they use that symbol mu in your textbooks, they're trying to tell you that the average or the expected value is blah. Okay, so that's just to add on that this is also another notation. That means the mean. Okay, and in the next lesson I'll talk about the properties, like how it differs if I had e of a function. What if the variable was a function? What if it wasn't just a number? How does it change things? Okay, and then what if the expected value had a linear equation? How does that change things? Okay, so I'll talk about that. I'll talk about that in the next session until I can get through variance and standard deviation. So now we know the mean. If you remember back in year 7, you learned the mean, median, mode, and you got your spread of data. Yeah, you're still doing the same thing. The only thing now is we're looking into, if you've done further mathematics before, it talks about residuals. Yeah, talking about the correlation coefficient. That's what we're sort of looking at now. Okay, so let's have a look. Variance. Variance is the measure of the spread, is in how spread is the data in terms of distribution and its mean. How do you find the variance? And if I had to give you a visualization, this is one of the ways I normally describe it. Let's say that I was to graph our data in the sense that the amount of hours you study dictates the percentage score that you get for your exam. Okay? So let's say this is your percentage score for your exam and this is the number of hours you study. Let's say that I made an expectation that I said there was a linear expectation that I expect you to, if you studied 10 hours, you will get 100%. Okay, hypothetically. Let's say that is my model. That's my expectation, mu, or, okay? Let's say that if that is my expectation, but in the real data, you guys will get a particular data. You'll get, maybe you studied 5 hours and you get 90, something like that, okay? Let's just give you a couple of random dots. Let's say this is the actual real data. Okay? Would you say my what I'm guessing is accurate? Fairly accurate? Okay? Really bad? What would you say about my expectation, my prediction of you guys? Pretty good. Now let's compare that to this kind of dot then. What if I then said my data is like this? What does that imply? Compared to the previous dots, what would this imply? That my expectation is pretty spot on. It's very close. So what's happening here? Like, in terms of the number of dots, I haven't really tried to change the number of dots I've done, but it's the spread. Variance is the measure of spread. The wider the spread is compared to the expectation or the mean or what you expect, the less accurate it is. Okay? So how do you know if it's accurate or less accurate? What are you doing implicitly is this is what you're doing. You're saying, Mr. Tran predicted this. And the reason why you know this is more accurate is because the distance between your data and my prediction is less. That's why. Okay, so you can see each one of these datas, the distance is much smaller from my actual prediction. That's why you're saying it's very accurate. So if I ask you, how do you find the difference between your data and my data? This is called the residual. Well, how would you do that? You would say, well, if let's say, I know Jordan right here got 75% for studying 5 minutes. Okay? It's pretty damn good, yeah? And let's say my prediction for you at 5 minutes, I said you should have got 60%. That's my prediction. Then how do you find that residual? What's my percentage of error? You would say take his data, 75%, subtract it from my expectation, which is 60%. And that will give you a value. Okay? That will give you a value. Now, if you wanted to know on average for everyone's data whether my prediction, my error is good or bad, what you would have done is you would have then added the difference between these, added that, added that, added that, added that, added that, found all the differences, which is summing all of my residual and then dividing it by the number of data I have. So what are you actually doing? You are then finding the average of my error. The larger my error, the wider the spread is. The less of my error, the more accurate it is. That is the variance. But there's an issue to the variance right now. Can anyone see the issue to this variance? In what I'm describing, if you're just subtracting your data from my expectation, your data from my expectation, what's the issue here? You're going to get negatives. Now, if you're going to get negatives, potentially, let's say this person down here, I said that they studied 10 minutes. I'm going to assume that they're going to get 75%, but instead they get 60%. So according to what I'm showing you, it would be 60 minus my expectation, and you get minus 15. So I'm negative 15 off. Now, regardless, what I'm trying to say is whether I'm 15 above or negative 15, I'm equally as wrong. See, 15 up or 15 less, it doesn't make me any better just making a prediction that you are actually 15 more than what I predicted or 15 less than what I predicted. It is the same error. So what we want is we want the absolute value of this. We want the positive value of this. So the variance describes the spread, tells you how far the data is, how bad my sort of expectation is. But the problem with this is it's a net signed area, because if I only had two data to work with, if I only had expectation here and I had one that was 15 plus 15 off and one was negative 15 off, technically, if I asked you to find the average of this would be 0. So does that mean that my data is super accurate? No, it doesn't mean that. So that's why with the variance, it only gives you an idea in terms of it tells you the spread, but it doesn't tell you the accuracy of my errors in my prediction. So the question is, well, then how do you deal with that? How do you make the negatives or eradicate the negatives? This is where the standard deviation comes in. So this is what the standard deviation is, and I'm going to show you. Standard deviation is the square of your variance, square root of your variance. Or you can think about it as standard deviation being squared equals to variance. Okay, so if you squared your standard deviation, so the question is, why do we do that? Now, why are we squaring it? Because if you squared all your data, whether it's positive or negative, if 15, that was my error before, 15 squared will be equivalent to negative 15 squared, which is why standard deviation, when you square your variance, it makes it the same error. The problem with this is it is now out of proportion. That I made an error, like I made a prediction that was 15 off, but if you square that now, that implies that I made a massive error, which is not true. Okay, so standard deviation is a nice way to put yourself into categories. How much 68% of the data is in a certain point, or 98% of the data is in a certain point. But the variance tells you the spread. It tells you how far am I off, but it doesn't tell you how accurate it is. Standard deviation tells you how accurate it is. Now, if you look at the formula, this is the formula for variance, and it will apply, and I said the only one concept, that's the one concept I wanted to teach, because this applies to continuous, it applies to binomial, and it applies to normal distribution, same theory. So this one theory, what variance is, if you notice, E is the average. And I told you before, it is the average of my errors. How do you find the errors? I said take your data minus the expectation that I had. That's what they're trying to describe here. Right there. They're just saying take your data x minus what you expected, and if you square it, then you will eradicate that problem in the sense that you will not have negatives. So the variance will now be in your positive section. Okay, all positive, but the problem with the variance is it's all out of whack. Okay, it's all out of whack, it's all super large. So to get it back, you see if it was 15 squared, if you square it, it equals to your negative 15 squared. So this tells you your variance, but the problem, what is the problem with this? Is that now my error is way beyond what it actually really is. So the standard deviation is more accurate because if you square root this now, whatever that value is, if you square root that, that will bring it back to the positive value, which is 15. So you eradicated the negative. That's what the standard deviation does. It square roots your variance. You squared it at the start to make it large and make it all positive, but then you square root it to get the actual distance. That's why standard deviation will tell you accuracy, variance will tell you the spread. Okay? Any questions? Yes, Roberta?
Do they generally ask for percentages or values like that?
Oh, right. They normally give you a probability, and normally it's a value. So variance tells you, so when you solve for it, it'll tell you a value. It'll tell you a value, and even with the expected value, it tells you a value. It doesn't tell you a percentage, it tells you a value. Yeah? It doesn't tell you a percentage, it tells you a value. But when you're working the probability of something, you may use the expected value to solve for the chances of this happening, if that makes sense. Yeah? Okay? All right. Now, I am aware of the time. What's the time? 10:20. Okay. Just to put things in perspective, this is your distribution data. We call this your discrete distribution. Okay? So I've got negative C and C. My x variables are negative C and C, and I've got the chances of it occurring is 50%, 50%. The question tells you to find the standard deviation of x. Now to find the standard deviation, we said the standard deviation, which is given by sigma, okay, sigma is the square root of the variance. Okay, well I should just use variance here. So that was from the previous page I just showed you. Variance, how do you find the variance? Variance was find the expected value of your data minus your mean, what I expect you to get, square that so that you eradicate that negative issue. This is the variance. Square root that data because you've squared everything, it becomes a problem, so you square root it back to get the actual error. That's what they're asking you to do. So, in order to do this, your x data is this. You need to find the mean, because you don't know what the mean is. But we know how to find the mean. Expected p, I told you before, was equal to the sum of x multiplied to p of x. So I can find the mean. Then I can put it as an expression and find our standard deviation. So, here we go. So, I said we have to find the mean first. It's x times probability of x, which is given by negative c times 0.5 plus c times 0.5. So I get mu equals 0. Now, variance, which is sigma squared, I said that it was take your data minus what you expected, and then you square that to avoid the negative. So that's what I'm going to do here. X, which is your data, but then the mu we know was 0. So therefore you got e of x squared. Well, how do you find e of x squared? E of x squared is just saying square this x value data and find the average of that. So this would be c squared multiplied to 0.5 and plus those two together. That's the average. And therefore you would get c. Or you, because you can find the variance, square root the variance. If that's the variance, square root the variance and you're set. Okay, so if you think about it, that was c squared and a half plus c squared and a half gives you c squared. That's your variance. And we know that standard deviation is equal to root of variance. Therefore, square root of c squared, which is c. That point. Now I'll carry on with the next session about these three terms again, okay? But read your textbook, 13D, okay? Very important. Year 12 concepts. Thank you. Yes. Oh yeah, the book? Wait, I'm just gonna stop the video.